So solid solutions are important because they they are dependent on the temperature variations within the crust or mantle. Okay, so the temperature is a determining factor, right? It's a very important factor that can cause uh, these solid solutions to occur in different minerals, right? So these different, I mean, every mineral does not facilitate solid solutions. It depends all on its chemistry, right? Whether the mineral structure is able to replace atoms or ions, right? So that is very important, right? So a series of compositions you can have as solid solutions, right? Uh, it can be even, I mean, some elemental groups also, right? Groups of elements can also replace some positions in the molecule, so that solid solution can take place, right? Those are complex solid solutions. We are not considering them here now. Okay, so if you can remember, most of the solid solutions are highly favorable if the replacing atoms or ions are in equal size, right? Equal size in the sense like 15% difference is allowed, right? It's, I mean, naturally within 15% of difference might be okay to say that they are in equal size, right? Like for example, these these ionic radius, right? In angstrom, it's given here. You can see they are closely related. They are closely similar, so that they can easily replace to each other. And also the amount of the solid solution or the degree of solid solution depends on several factors, like the size, charge of the ions involved, right? Because it has to decide whether just one solid replacement is enough or multiple replacements are necessary, right? To make sure the charge is balanced. That is also important. And also the temperature and pressure, right? So these factors are very important for the degree of solid solution, right? That means the amount of solid solution to happen. It can be variable, even though in a single rock, different minerals can show different amounts of solid solution, right? Even even the same mineral can show different amounts of or variable amounts of solid solutions, because sometimes these factors are not homogeneously distributed within the domain, either crust or mantle. Okay, so therefore there can be changes. That's why when you see thin sections, uh, you can observe different compositions, right? For example, if you take a thin section and analyze it by microanalyzer, electron probe microanalyzer, for mineral chemistry, you will see different amounts of solid solution I mean, from this displayed from same type of minerals, right? If you take pyroxenes, they will show different amounts of solid solutions, right? So all depends on these factors. That's the reason. And we discussed there are three types of solid solutions, right? Three types of solid solutions: substitutional, interstitial, and omission. Okay, substitutional, interstitial, and omission solid solutions. So the simplest one is the substitutional solid solutions, where almost similar sized ions are replacing in the structure, right? You can call it solvent atoms and solute atoms. Solute atoms are the foreign atoms that is coming into the molecule, right, for as solid solutions. So if they are very similar or almost equal, right, within 15%, typically, but other changes can also happen. That is called substitution of solid solid, because there is a direct substitution. Instead of one place, one ion, another a similar type of ion is replaced, right? And the second type is the interstitial one, interstitial solid solution. That is the solid solution where it takes place, uh, the solute atoms or the foreign ones go into interior of the molecule, where some spaces are there, right, in between. So there is no direct replacement happening, but instead what is happening is a new ion is coming into the structure uh, to a place where there is some space, right? So in this case, there can be some distortions happen to the structure. It's possible. And the other one is the just a minute. Omission solid solution, where a higher charged atom is replacing the structure, so that one or two ions has to remove from or omit from the uh, from the uh, from the molecule, so that sometimes it might produce some kind of spaces, additional spaces within the structure. We'll see them again later. And you can see here the first type, the substitution of solid solution, where fosterite and phthalate, the most prominent type of solid solution, uh, which is taking place within the olivine structure, right? Iron magnesium solid solution. So you can see again iron manganese substitution, where you can see the rhodochrosite and siderite formation as end members. Okay, so in the previous case, sorry, the fosterite and phthalite are the end members. Okay, so here manganese and iron. And we discussed that sometimes you have to have a couple substitution. Substitution, that means multiple cations or anions. Mostly this is happening with cations. Okay, replacements happen, multiple replacements. For example, instead of aluminium, there can be two substitutions taking place, calcium and titanium. Okay, two replacements can take place. So here, instead of two aluminiums, okay, instead of two aluminiums, there can be one calcium and one titanium replacement. That is also substitution, but it's coupled substitution. Another example here, calcium magnesium. There can be sodium aluminum replacement, right? So this is happening in diopside and jadeite. Diopside and jadeite. You can see instead of these two, calcium and magnesium, sodium and aluminum replaces. So this happens usually when the pressure increases. Jadeite is especially a pressure sensitive phase. So the normal dioxide can be changed to jadeite when a sudden pressure increase is happening, especially in subduction zones. So this coupled substitution take place in that case. Okay, and you can see anorthite, albite, anorthite and albite change, right? So calcium aluminum is replaced by sodium silicon, right? Sodium silicon. Here you can see Si is 2 here, but here Si2, sorry, Si3, silicon 3 atoms there. because you have monovalent cation here, right, instead of bivalent cation which is available there. So 3 plus 2 5 and 4 plus 1 5, right? So this is another couple substitution occasion. So interstitial example, as we mentioned before, some solute element atom which is coming into the structure into some spaces available within the structure, right? Interstitial means within the regular atoms, metal atoms, right? Regular atoms. So it makes it needs some gaps to replace within the structure. So it all depends on the shapes of these ions, right? Not every atom or ion gives this type, give rise to this type of solid solutions. Right. And one again, coupled interstitial solid solution can also take place, which I did not mention at the previous time. We mentioned only the substitution of solid solutions where coupled solid solution happens. But in the case of interstitial solid solutions, also coupled solid solution can take place, because some substitution is necessary to retain the overall neutrality of the component, of the compound. So one example is here, tremolite, and you can see here it changes this calcium, right? This calcium is there and magnesium is there. So you have some sodium is coming into the structure, right? To change its composition. And you have now aluminum also inserted there, right? So it gives you the balancing, right? So here this is 4 Si4 and sodium aluminum all together makes it 4. Okay, right. So here no aluminum, but here you have aluminum. Okay. Here no sodium, and here you have sodium. Okay. So, but this is taking place within the molecules, not direct substitution. And this is happening because it is happening as an interstitial solid solution. And another example here, when some vacant, that means space is available within the molecule. So the spaces available in between makes this solid solution happening, right? Beryl is an example, right? This is the normal beryl composition. And for silicon, this is 4 plus, beryllium 2 plus. So it can make some solid solution with one of these, right? Usually one of these cations, potassium, rubidium, or cesium, or multiples of them, right? So anyway, it should be some 2 plus. It should provide 2 plus charge, either 2 potassiums or 2 rubidiums or 2 cesiums, or even a combination of these, one each. That's possible, right? So it will produce an interstitial solution behavior there. So when we come to omission solid solution, so we mentioned that usually it happens with the highly charged cation. It places two or more cations to balance the charges. Okay. So in this case, there can be some gaps produced. For example, this structure, if this is the original structure, this one, and this is after the solid solution. So you can see, uh, because highly charged cations replace the molecule some places. So you will you don't need some ions existing there. So they will be omitted. In that case, you will find some spaces, right? You will find some spaces where the ions which have been omitted from the structure, right? So some spaces are uh, created there, okay? Some gaps in the crystal structure. So it can cause reducing the volume reduction in the molecule. Some volume reduction can take place, right? So if the volume reduction is facilitated, usually it's a stable, it's taking place towards a stable direction, because energy wise, the reduced space is more favorable. Okay. So that, I mean, entropy inside the molecule, right? Energy, it's more stable for the molecule. One example, so instead of these small cations, right, potassium, in Amazonite is one of the feldspars. Okay, Amazonite is one of the feldspars. So you know, potassium is there in K orthoplace in K feldspar. So instead of two potassium ions, one large lead divalent cation can come into the solid solution. So it can make a different composition where you don't have potassium any longer. Instead, you have some lead, right? So Amazonite is lead bearing one. It's a very bluish, greenish feldspar, very beautiful feldspar. You can find it in some places in Martale areas, right? So it will make some omissions of potassium. And lead is going into the structure, so that there will be some spaces generated within the structure. Okay. So this can usually happen in feldspar group of minerals, right? This is how Amazonite is formed. And another example is chalcopyrite and pyrrhotite. Chalcopyrite and pyrrhotite, all those two are sulfides, right? Those are two types of sulfides. So chalcopyrite, you have CuFeS2, where Fe is divalent, okay? And it can substitute with the large cation, ferric, the highly charged cation, ferric, will be replacing there. Like in the previous case, what was replacing? Divalent, highly charged lead was replacing low charged potassium, right? Here, ferrous is replaced by ferric because ferric is highly charged. So it will produce some kind of a different structure. You can see here some spaces can be created after modification, right? So you can see these joints are no longer available, so that you have a space here, right? You have a space there because some of these ferrous are gone, right? Because this is omission solid solution. Please input your registration numbers in the chat box to mark the attendance. Okay, so you can see physically the change, the difference, the chalcopyrite and pyrrhotite, right? This is pyrrhotite and this is chalcopyrite. So after replacing ferric there, okay. So these are omission solid solutions. I think now you can remember the types of solid solution, because solid solution is anyway changing the composition of a mineral in the solid state conditions, right? Always remember this all happens in the solid state conditions as a result of change of temperature, pressure, and also other factors are important, whether similar size cations to replace is available or not, or the charge uh, similar or higher, which is available or not, like that, right? Depending on all these factors availability, the type of solid solution is naturally determined, right? Whether substitutional or interstitial or omission type of solid solutions. Okay, so now I think you can understand towards the increasing side of temperature. Always remember, towards increasing temperature, uh, this solid solution is favored, right? So as soon as you drop the temperature, no longer solid solution is possible, right? So it's a driving factor. Temperature is a driving factor for the solid solution. So as long as the temperature increases there, solid solution can take place, and these reactions can be reversible because you see, depending on the direction of temperature, to some extent these are reversible, not 100% reversible, right? So reversible means you can expect the reaction to come back to the original direction, right? Original situation. So solid solution is we simply, in simple terms, it's a mixing, right? So instead of one atoms, another one or two atoms are mixing with the molecule, right? So if it is reversible, uh, you should be able to unmix the component, right? Unmix the components that contributed for the solid solution, right? For example, if you mix sodium and aluminum there instead, so you should be able to remove these phases also out, right? But of course, it will not produce silicon, right? Sodium and aluminum will not reversible, in the sense it will not produce directly silicon from out of all the molecules, right? All that ions. But what happens is some kind of further replacement with silica can be taken place, right? Provided that silica is available, right? So that is what is happening, right? So in this type of situation, even for example, forsterite, phalite, right? So this reaction, I mean, magnesium and iron can be mixed together, and it can be unmixed also when it is reversible, right? This is straightforward, it is possible, but in the case of like interstitial or omission case, where entirely different ion is involved, right? uh, it might not uh, be possible for making it reversed reaction, because of they are different from each other, entirely different from each other. It's not just the ratio maintenance, but in the case of phalite forsterite, it's just a matter of maintaining the iron and magnesium ratio. So that is possible under diffusion situations. Iron magnesium ratio can be maintained, adjusted within the molecule. But in this type of solid solutions, unless you have extra or additional or excess uh, cations of, for example, silica here, right? You can't have that reaction reversed, right? So if excess silica is available, that means if you have a lot of quartz there, right? If you have a lot of quartz, in your rock, then some silicon from quartz can be contributed, right? That is possible. Otherwise, it won't get reversed. But normal iron magnesium or calcium magnesium like replacement, the cationic ratio can be adjusted if it is a substitutional solid solution, because the cations can exchange. Substitution means exchanging. Okay, but these are very different, and also you see volume reduction is also taking place, so it's very hard for the molecule to come back to the original situation. So these are not really uh, uh, reversible unless you have additional material available, right? So it's hard, but not 100% reversible. To some extent, partially it can take place, right? But substitution of solid solutions are uh, very comfortably reversible. So what is this reverse reaction called? That means mixed component we call solid solution, and if it is reversed when the temperature drops, for example, if it is reversed, what should happen? These components should unmix. That means, for example, like you make a sugar solution, you dissolve some sugar. Okay, you dissolve some sugar and salt both in water, right? And make a solution, right? So it's like a solid solution, but it's in the liquid form anyway. But you just consider it's a solution which was made using sugar and salt. You dissolve them in water. Now it's a mixture, right? So if you want to reverse it, if you want to unmix it, then you should be able to separate sugar and salt at a certain point, right? So that is a reversing of that particular action, right? So this is possible mainly for substitution and solid solutions, where this reaction is favorably reversed as soon as the temperature drops. That means sudden cooling. If sudden cooling happens, within the rock system, uh, this can take place. Usually associated with isobaric conditions, right? Pressure might not be changing. Pressure is constant, but temperature drops, right? So this is kind of a very unique type of requirement. We call that technically as isobaric cooling. Isobaric cooling or isobaric cooling. That means at a constant pressure, we cool the system. So you will have an unmixed component. That means your original solid solution has got reversed, right? So this one we call exsolution, right? So this exsolution process is actually the opposite of solid solution. So this is happening when the temperature drops significantly under constant pressure conditions, right? So sometimes exsolution can take place until the components are entirely unmixed, right? That is possible. So this unmixing we call exsolution, exsols, right? The conditions change. Conditions change means the temperature changes, right? So usually it is favored by isobaric conditions, right? Otherwise, it's just very. It might be reversing, but not very prominently showing the unmixed components within the rock, right? So in some rocks, some minerals show these solutions. You have seen them with the microscope, I'm sure. They show the separated phases, right, from different domains, discrete domains, right? So inside the mineral grain, right? So, so they appear as lamellae, so lines of zones, very tiny or very narrow zones in a mineral grain, right? So we can see the simply solid solutions in feldspar, right? In feldspar, we know perthite is a exsolution, right? It's one of the exsolution types. So their host grain is potassium, right? K alkali feldspar, right? For example, here, if you take this as the perthite, this should be alkali feldspar, right? Potassium feldspar, and these lamellae, which represent unmixed components, right? Sodium unmixed components there, right? So if the temperature progressed very well, uh, the solid solution will go up to the complete solid solution status, so that we will see only K feldspar in the mineral, right? So everywhere it should be K feldspar. But if sudden temperature drop is there, you will encounter this type of lamellae, right? So that means it's getting unmixed. So you can't have entire unmixing within the grain, because these take time. Probably by that time the rock may have exhumed to the shallow levels. So the the exsolution process may have already stopped, right? It's kind of arrested the exsolution process. So if in any case, if it was allowed to continue, then you will see, instead of these lamellae, entirely white zones, very big white zones, or entirely the K feldspar is covered with this perthite. Okay, so if it continue, but normally it does not continue, because by that time the rock has come to the shallow levels, uplifted already. So very shallow means a very low temperature and pressure, and no reaction, nothing happens there any longer. So this is anyway unmixing. So this is opposite of solid solution, and we call this exsolution, right? So there is another possibility, we call it antiperthite. In antiperthite, the host is, instead of K feldspar, the host is albite. Okay, the host is albite, and there you can see lamellae of K feldspars. So that is what you call antiperthite, right? So perthite, antiperthite both represent exsolutions. These are thin section photos for exsolutions, and you can see uh, the hand specimens given here showing these exsolutions. See these lines, very tiny lines you can see, right? Parallel lines. These are zones of exsolutions, right? So similar to these places in thin section you observe. So here also you can see some lines with different solid solution, different degrees of solid solutions. So all these lamellae represent the exsolutions which was derived from original solid solutions within the mineral. Okay. Okay. The similar type of solid solution can be there from pyroxene. right? Sorry, exsolution can be observed in pyroxenes. Where OPX and CPX can be there as host and the newly formed lamelles, right? For example, this is OPX zone, and this blue is the CPX, and these lamellae are OPX again, right? So you can see here uh, there is a relatively large area displayed here. So that means the continuation of the reaction has happened there, right? So that it could make almost entire area to convert into one of the other phases, right? So here again we have exsolution lamellae, right? So these are exsolution lamellae, and you have a host OPX here, and the Hans-Wisman also shows these structures. Can you see those? Maybe not very clear like in the previous example. There you can clearly easily see earthite, right? But here it might not be very clear, but still you have the zones of replacements, right? Unmixing. These are exsolutions. Okay, do you have any questions? Do you have any questions regarding the solid solutions and exsolutions? Okay. So now we will move to see a little bit on the graphical representation of mineral compositions. This is nothing, nothing new. This already you know. It's just a matter of showing the composition in terms of two end members. Okay, so if we have two end members like here, for example, two discrete end members, silica and alumina, and in between you can have aluminosilicate compositions, right? This is aluminium, this is silica, right? So ideally we will have aluminosilicates in between. Okay, so you can denote different amounts after determining it by electron microprobe. So you need analysis, then you can determine, for example, silica here, like 65% of silica, and aluminium like 35% of aluminium, right? So like that you can represent. So kyanite is an example for an aluminosilicate, right? So another kyanite can be a little bit enriched in alumina, right? So it is going a little bit further, right? Like here, it goes a little bit further than the previous kyanite shown here. Okay, so this indicates the fact that I mentioned at the very beginning. The same mineral can have different amounts of solid solutions, right? So the degree of solid solution is entirely dependent on the four factors that we discussed. Okay, the size of that ion, the charge, and pressure, temperature, availability, right? Conditions. So in case if you can unmix this kyanite composition, right? If you can unmix this kyanite composition, it's very hard, right? In reality, you can separate out silicon to one side and alumina to the other side, right? So these are the two end members for this aluminosilicate. So you have silica end member and aluminum end member. So when you mix them, you can produce kyanite at variable compositions, right? So it can be the weight percent or molecular percent. Uh, anyway, it represents a mixture of composition, right? So this is a graphical representation of two n-member mineral compositions, right? Two n-member. So when you have another one, definitely you will have to go for a triangle, right? Because the third one you have to accommodate somewhere there, right? So we'll see that also here you can see magnesium and silica, SiO2, and calcium. Okay, so you have three N members there, and depending on its composition, uh, you can uh, you can uh, you can show its composition. For example, the dot represented here, right? The composition represented here. If you count how much silica is there, right? So silica variation 100% is here, right? 95% is here, 90% is here, 80 is 85 is here, 80 is here. Sorry, it's changing by 10, right? 1, 2, 3, 4, 5. Oh yeah, yeah. So this is 100, and this is 90. This is 80. This is 70. This is 60, and this is 50. So you have 50 weight percent of silica. So what about the magnesium? Magnesium here 90, 80, 70, 60, 50, 40, 30, and 25. Right here, it's 25. So magnesium is 25. Calcium should be again 90, 80, 70, 60, 50, 40, yeah, 30, 25, right? Because this is 20, so 25 is here. So you have 25 calcium. So if you want to plot 25 each, 25 calcium, 25 magnesium, 50 silica, then it comes this place to this place. Okay. So similarly, you can have like 33, 33, 33, all three components. So it is coming into the central position here. So these are the three n-member component representation, right? So three components, if you have in your solid solution, the mixed mineral, if you have three components, that means magnesium, silicon, and calcium mixed together, then you should be able to show that particular mineral here in this way. Okay, so these are graphical representation of minerals. Okay, so actually these are called ternary diagrams, right? Ternary diagrams because you have three members, three compositions, three n members. So you can get the feldspar ternary diagram here. Feldspar ternary diagram. There you can see the compositional variation of feldspars, alkali feldspar series, and plagioclase feldspar series. Alkali feldspar series and plagioclase feldspar series. So those two are n-member compositions, right? So those two are solid solutions actually. So you may notice that there is a huge area here which does not have any feldspar composition, right? So this is a miscibility gap. So you don't get mixed these components each other, so that it plots somewhere here, right? Like in the previous example, and no composition of feldspar coming into this point. That means no feldspar like this in terms of potassium, sodium, and calcium. Okay, right. So it's a uh, missing area of composition. Right. So another example by pyroxene. So this is pyroxene composition. You have seen this diagram before. There you can see magnesium, iron, and calcium. Magnesium, iron, and calcium as in members there. So for orthopyroxenes, you can have it represented in this place, right? OPX from hypersteam to uh, ferrocylite. Okay, from hypersteam to ferrocylite. That means magnesium and iron end member compositions. Magnesium and iron end member compositions. And then when you have calcium also in the pyroxene, you call it CPX. This is OPX. And then you have CPX here. You have some calcium component also in addition to iron and magnesium composition, in addition to iron and magnesium. Okay, so you can clearly see uh, they are plotting in different places. So you already know in these places there are no compositions, natural compositions, right? So that means that represents miscibility gaps. That means kind of unmixing. You can't mix within that region, non-mixing area, right? Not unmixing. It's like non-mixing area. Right? You can't mix components in those areas. So you have orthopyroxenes and clinopyroxenes solid solutions. So CPX solid solutions from calcium to iron, dioxide to hedenbergite, and also augite with variable composition of calcium. And for orthopyroxenes, you have magnesium to iron, magnesium iron change, exchange. Right? So pigeonite is one exception. It's neither OPX and O. It's neither OPX nor CPX, right? But at very high temperature, it can absorb some calcium. It can enrich some calcium so that you have a little bit above uh, calcium composition there in pigeonite. Still, it can exol. Pigeonite can exol to OPX. That is possible, right? Exol means unmixing, right? Remember? So it can make some exsolutions, some lamellase within OPX, forming pigeonite, showing unmixing nature. Okay. Do you have any questions regarding this representation, graphical representation? When you plot, it's manual. Plotting manually is very hard. It's not easy because you have to calculate three components uh, to uh, to represent the percentages and then get into the plot. But now we have some macros for Excel and also some softwares for direct plotting of triangular diagram. So it's just a matter of giving the three component compositions. It will automatically generate the plot for you. Okay, so therefore it's easy. Okay, this is end member three component n member representation. You can also represent forced right phalite also in a binary line, right? So this is a linear representation, whereas this one is a triangular representation, right? Ternary representation. Okay, right? Any question? We didn't talk about the wollastonite, right? Wollastonite is there. What is wollastonite? It's a calcium N member, right? It's a calcium N member of pyroxene, but actually it's not a pyroxene. It's not a real pyroxene because I think you can remember we discussed about uh, pyroxenoids, right? Pyroxenoids, remember? Some structural changes to the chain silicates because pyroxenes are inosilicates, right? But some of these chains are distorted. If you can remember the angstrom, the length between the repetitive units, because for a chain silicate you must have a repetitive unit, right? It's repeating one after the other, right? But when this repeating unit is distorted, uh, it's like changing the distance between two molecules, so it gets distorted, right? So pyroxenoids are formed as a result of that. So if you have some pyroxenoids like wollastonite, uh, it will definitely come over here. Okay. So other minerals also you have this type of ternary plots. Most of other uh, minerals which have a little bit complicated structure, having more than two uh, mixing components, right? When you have more than two mixing components, definitely you will have to go for this triangular plotting. Okay, right. Now, I will show you some simple calculation for formula determination. So we call it formula determination because, you know, once solid solution takes place, there can be variable amounts of cations, right? So for example, here 33 weight% magnesium, 33 weight% calcium, 33 weight% of silicon. Here 25, 25, 25. Like. So likewise, the solid solutions are having variable compositions, different compositions. So depending on this solid solution nature, the amount of cations involved there. For example, here 33 weight% of magnesium is there, but here 25 weight% of magnesium is there, right? So the involvement of cation is different. I mean the mole amount, how many moles involved there in forming that molecule is different, right? So that determines the chemical formula for that particular mineral, right? So if they are ideal, then for us it's very easy to represent the formula. For example, here posterite, this is the ideal chemistry, right? No iron. This is just N member, so you can just simply put it as Mg2SiO4. But similarly, phalite also. But when it comes to plot in the middle, right? It's very hard to assign exact composition there unless you measure it and recalculate it, right? So it's hard, right? But for the things you plot in between, so you have instead of just one magnesium atom there, you have iron also incorporated there. It's a mixture, right? So you have iron and magnesium mixed there, but you don't know I mean to which extent these ionic involvements are they are in the molecule. This is the ideal situation, but once a solid solution is happening, it will reduce the amount of magnesium and incorporate some iron, but you don't know how many cations or cationic ratios which can represent your composition. So for that, we need chemical analysis. We need chemical analysis of the mineral, and then we have to convert their percentages, right? So for example, feldspar is analyzed, right? The ideal composition of feldspar is here, right? So in the textbook, you will see the feldspar composition like that, right? Calcium, sodium, potassium, iron, aluminum, SiO4O8. This is certain as SiO4O8, right? But we don't know whether this is just one, two, how many moles of elements involved there. You don't know that, right? That can be determined after analysis. So suppose some feldspars in a thin section was analyzed, and you have a composition of oxides. Usually, the machines uh, give the oxide percentages, right? Of course, percentages can also be taken, but for um, for more precise representation, we prefer to have oxide percentages, because usually these cations are bonded with oxygen within the molecule. So therefore, it's advised to determine its oxide percentages rather than directly getting elemental compositions. So you get oxide percentages. These are in weight percentages, right? Weight percentages. So you have to know. Okay, so this is determined by analysis. Let me show you this one. This set of data is coming after analysis. Okay, analysis means EPMA, electron probe microanalysis, right? That is the most convenient way to analyze minerals, right? Even our SCM, which we have in our department at the first floor, can also do the same, right? But the precision is not enough, right? But formulary calculation, that's okay. Formulary calculation, that composition is okay, but advanced applications like thermobarometry, pressure temperature determinations, calculations, we need very highly precise data, even up to the first decimal point, correctly measured. So for that, we need more precise determination. So therefore, we go for an EPMA, right? Electron probe microanalysis analyzer. EPMA, electron probe microanalyzer. This is an equipment we can use for mineralogical composition determinations in thin section. You can directly insert a thin section there and measure, right? It measures through an electron beam, bombarding an electron beam onto the sample. Sample is not getting damaged. Okay, electron beam doesn't make any harm to the material surface, right? Unless iron beams, like iron beams, can harm the sample. That means it's a destructive method. But the EPMA is not a destructive method. It's a non-destructive method, right? So you measure it, right? You measure it and you get SiO2, aluminum, ferrous or ferric, so potassium, sodium, like everything you get in as a list, right? So now we make a table. You can make a table in Excel and you input atomic weights of these oxides, right? That you can find from a textbook, right? From a textbook, you can find the data for the atomic weight, right? So you input that there in the table, and then you have another column. You need another column where you show the number of cations in oxide, number of cations in the oxide. So you can see in SiO2 here, you have only one cation, silicon, right? So you have only one cation. But in the case of aluminium, in this oxide formula, you have two aluminiums, right? You have two aluminiums there, right? So cations two, right? So likewise, you mark the cation number also in this table, right? So then uh, you count number of oxide, I mean number of oxygen O2 minus in the oxide, right? So you have two oxygens there, right? You have two oxygens, two here. Alumina, you have three oxygens. Ferric oxide, again you have three. Every other things, you have only one oxygen atom there, right? In the formula, per formula unit, per formula unit, right? So this is just one formula unit. So for that, how many oxygens are there, right? So you mark it also. And then you have the data, oxide weight percent measured by EPMA, which is also inserted into the table, because you can easily do the calculation. That's why I'm asking you to tabulate it. Then number of moles of oxide in the mineral. So number of moles of the oxide in the mineral, you can determine using the atomic weight, right? You have the weight percentage, you have the atomic weight, and then you should be able to find out the number of moles of oxide they are in the uh, in the mineral. Okay, so you divide the weight percentage by the atomic weight, right? Then you will end up with some numbers which indicates number of moles of oxide, because we divided it by the atomic weight, right? So that will give you the number of moles. So oxide moles, number of oxide moles, remember, right? Number of oxide moles means number of moles of this entire component. Okay, not just oxygen or anything. The number of moles of this oxide is given there. Okay, and then mole percentage you can calculate of the mineral mole percentage. For example, mole percentage, because you have the total moles here, right? You have the total moles here, and you have each and individual uh, number of moles there. So then it's easy for you to calculate the mole percentage, right? You can calculate the mole percentage using these two numbers, right? So you get 73 for silica, 12.8 for aluminium, right? Oxides, right? Mole percentage. So you have the total here, you have the each individual moles, and then you calculate the percentage of that, right? So it will total, it should sum up to 100 if you made it correctly. Uh, the advantage of EPMA is this actually. It indicates, it analyzes everything. It analyzes whatever is available within the mineral, right? So that means it should come to 100 totally, right? It should, ideally it should come to 100, but sometimes when you have some water molecule, for example, if you analyze hornblende, there are so many OH or halogen components there, right? So those are not measured by the EPMA. Anions cannot be measured by EPMA, right? But all the other cations will be measured, so that you will end up with 99 point something, right? 99 point something. But if you do the same thing using SCM, it will sum up everything to 100, uh, considering what you have selected as elements, right? In the SCM, you have to select the elements. For example, if you want, if you just select silicon, aluminum, and iron, or only these three elements, if you have selected those three, it will calculate the composition in terms of these three, right? So that means these three will be summed up to 100, right? So it will give you some value, assuming that only these three elements are there in the mineral. So that is the disadvantage in SCM, right? SCM cannot account for all the elements unless you specify them to analyze, right? That is the problem. But EPMA, it will definitely give you all the elements available because it has a separate calculation system of cations. Right? So that is the big disadvantage in SCM, right? So in SCM, you might get ferrous like iron oxide 80, say 60, right? Like here, and aluminum 20, and silicon 30 or something, no, 20, right? That will give you 100. But actually there are other elements also, calcium, some weight percentage, right? So if you compare this composition with real analysis from EBMA, uh, you can see it's a disaster, right? So SCM has very good advantages for different purposes, but EPMA also has its own merits and demerits. Okay, so for mineral calculation, formula calculations, and also for thermobarometry, we must use an EPMA, right? So that's why we use EPMA for this type of analysis, right? Anyway, so you get the mole percentage of oxides there, mole percentage of oxides there, and then you find out the moles of cations in the sample, right? The moles of cations, right? So we will take one by one cations. So out of oxide, silicon oxide, SiO2, you can find out how much silicon tetravalent cations there are in the molecule, right? Moles, in terms of moles. Aluminum, how much? Ferric, how much? Calcium, how much? Sodium, potassium, like that, right? So how much is that? You have mole percentage of oxides in the mineral. You calculated already. For example, silicon, SiO2, 73.83. Okay, so how many silicon elemental moles there in the molecule? SiO2, if you have SiO2 1 mole, you are supposed to have silicon also 1 mole there, right? So here, how? If you have 1 mole of alumina, 1 mole of aluminum oxide, you are supposed to have 2 moles of aluminum there, right? Here, calcium, if you have 1 mole of calcium oxide, you are supposed to have 1 mole of calcium cation there, right? Divalent calcium there. Understand? If you have uh, 1 mole of sodium oxide, you should have 2 moles of sodium cations there, right? So likewise, uh, you must have this number of moles of oxides in the mineral comparably calculated, recalculated to represent its elemental cation moles, right? So here you can see the silica SiO2, you had 73.83 mole percent. So then elemental wise also you have the same number of mole, right? But in the case of aluminum, you have 12 mole percentage is there, but in the formula you have 2 moles of aluminum there, right? Aluminum 3 plus cation. So then you have to multiply it by 2 to get the aluminum moles there represented. Ferric, again you have twice. Calcium, you have the same amount. Sodium, you have you have again twice. Potassium also you have again twice. So likewise, you get the moles of cations in the sample. Moles of cations in the sample you get here, and you can sum it up also to see how many total moles of cations there in the sample, right? Right, and then you have to find out how many moles of oxygen, have contributed to each cation, because you have cation number of certain number of moles here, and to that how many oxygen moles should be uh, accommodated there, contributed there, right? So see the molecule, for one cation, you have two oxygens, right? For one cation, you must have two oxygens. So then for 1 mole of silicon, you must have 2 moles of oxygen, right? So, so then you have this number of moles, right? You have this number of moles. So you must have double the uh, amount as a number of oxygen moles, right? You can have double. And aluminium, for 2 aluminiums, you have only 1 oxygen, right? Then for 1 aluminium, you must have half oxygen mole. So that means it's for in a given molecule, you must have 1.5 times of oxygen uh, for representation, right? So here you have 38.2, and then ferric also same, right? For three, sorry, for two in the aluminium, two Al2O3, right? Remember, this three is covered by this my drawing. That's why confusion comes. So every 3 oxygen has two related with two cations there. So that means 3 over 2 means 1.5. Okay, 3 over 2 means 1.5. So therefore, you have to multiply it by 1.5. Similarly, for ferric also. Calcium, similar, same, nothing, no difference. Sodium, you have half, because every 2 sodium is associated with 1 mole of oxygen. Potassium is also same, right? Half, it should be half, right? Because every 2 potassium, 1 mole of oxygen is there, right? So every 1 potassium, there should be half oxygen. So you have to multiply it by 0.5. Right, now you have molecules of number of oxygen molecules there, number of oxygen moles there. So you can sum it up also because we need it later, this summation, right? And now you have a formula without considering the oxygen. You can simply represent the formula like this, because you had originally calculated uh, number of moles in cations, right? Number of moles in cations you calculated here as 125 as a total, each like this 73. So then silicon should be, because this is the general formula, right? This is the general formula that you have to consider. So silicon here, this one, silicon, this one, how much is there in your measured sample, because we measured the sample already, right? There you had silicon 73.83, right? That number of moles are there, because in a chemical formula we represent the mole numbers, right? This SiO4 8 means small numbers, but we don't know the cation moles. That's why we wanted to analyze it, right? So if you take it the entire percentage, you can put silicon. See here, 73.83, right? Aluminum, how much? 25.86, right? You can put 25.86. So likewise, you can put everything what you got there. But actually, in the ideal formula, how many oxygens are there for the feldspar? 8, right? Here you have 8. Usually we keep the formula simplified, right? This is not a simplified representation. So we want to have the minimum representation. So therefore, we have to recalculate these mole numbers so that it corresponds to 8 oxygens. So for that, you have to take this ratio, right? So for entire number of oxygen moles which you require for representation of each of these cations is 200.38 according to this analysis, right? Then to represent the ideal composition, that means 8. That means you need 200.38 number of oxygen moles to represent the entire molecule here, but we need to recalculate how much is necessary for 8. So then for 200 this much, and for 8 how much proportion you have to take. So you have to multiply by this factor. This is kind of a factor, the above formula, each and every number, right? So this each and every number should be multiplied so that you will get the representation for 8 oxygens, right? So you get silicon if you multiply this 73.83 by this ratio, by this factor, you will get 2.95. You get 2.95. Okay, you get 2.95. Right. So likewise, you have to recalculate. This formula so that you get the minimum number of moles of ions required to represent this particular mineral. So in this case, feldspar. So you get silicon 2.95, aluminum 1.03. Likewise, you get some numbers, right? So that is the simplest formula you get from this analysis. So you will finally end up with the formula given like this, which corresponds to 8 oxygens. So remember, this is 8 oxygens. Okay, how many silicon you need? 2.95. Aluminum, this one. So this is the real stoichiometry of that feldspar. This is the real stoichiometry of this feldspar. Okay, so we need this stoichiometric formula to calculate some compositional variations required for some advanced calculations, right? So actually, this is the real formula. I mean, for the naturally occurring feldspar that you collected from a quarry and measured, its real formula is this one. This is a generalized formula, ideal type of formula for feldspar, but in the reality, by composition and analysis, you get that formula slightly different from the empirical formula, right? Here, everything is one, right? Everything is one for the ideal formula, but you know, in the nature, it is not one really, right? You get different numbers. Calcium, for example, 0.03 in this particular case. Sodium 0.62. So these are mole numbers. Okay, these are more numbers. If you analyze another feldspar from somewhere else, you will again see some different numbers, right? So that is the real solid solution behavior explained uh, by the natural analysis. Okay, right. So this is very important, which we call the formula recalculation. Actually, this is a recalculated formula, right? By means of actual analysis of chemical components available within the molecule. So these are actually the mixed cations, right? All these cations are mixed within the feldspar. So that is the solid solution actually. So we measured it uh, measured it using EPMA and then recalculated to get uh, the precise formula. So this is the precise formula you get from chemical analysis. Okay, so this type of conversions we have to do for example, to see the site assignments in a molecule, right? Site assignments in a molecule, and also for thermobarometric calculations. That those are the things that we consider as advanced calculations that we need the real formula, the stoichiometric formula for our further determinations. Okay, so this is how we do this formula recalculation, right? So all these things are related with solid solutions. So this is important. Even non-solid solution minerals also you have to do formula recalculation after actual analysis after EPMM. Okay. So this is how we do these mineral calculations. Using an Excel worksheet, you can easily do this calculation. Okay. So do you have any questions? Any questions related to this content? Just to summarize what we have done today, we reminded about the solid solutions, right? Types of solid solutions. What did we have? The solid solution types. Yeah, substitution of solid solutions, and then interstitial solid solutions, and then omission solid solutions. And we considered about the single substitutions as well as couple substitutions. And in some cases, interstitial, sorry, omission solid solutions also have some couple substitutions, which might not be reversible successfully, but substitutional solid solutions are reversible to considerable extent, right? Okay. And then we discussed about the formula, the representation of components of a given mineral in a linear representation or triangular representation, ternary plotting, right? So that will give you the composition interpretations, because in petrology we may have to use these ternary diagrams frequently to interpret about rock's evolutionary history. So this is an important factor. Okay. So then we discussed about the mineral formula recalculation, right? So this mineral formula recalculation is also important because that helps us to know the actual molecule, actual mole percent, actual mole numbers represented by its stoichiometric formula, right? So the real stoichiometry represented by a natural sample can be achieved by doing this process, right? It's a little bit complicated, but I don't think that is difficult because with if you plot, if you tabularize them all in an Excel sheet, then you can do easily calculate it. Okay, right. So this is what we have to discuss for the time being. And I think I haven't covered or I did not conduct tectosilicates, descriptions on tectosilicates in the previous lectures, but I think it's nothing complicated for tectosilicates because tectosilicates are feldspars and quartz. Remember framework silicates, right? We covered all the other types of silicates, and I will leave you to self study on tectosilicates, right? Because that is the strongest type of silicates we have. Uh, I mean, it's because it's a framework. It's bonded as a framework type of a tectosilicate, so that it gives a robust structure. It's that's why quartz and feldspar remains unweathered or unaltered for long. Okay, compared to mica, pyroxenes, or other things, they will easily get altered or get weathered, right? But the tectosilicates remain very robustly, so that they will not change much uh, uh, with the atmospheric conditions, right? So I leave you for tectosilicates to self study. Apart from that, I think we have covered all the silicate types, right, in under the descriptive mineralogy in the previous cases. Then we covered solid solutions and exsolutions, and some examples we saw. Okay, so I think we can conclude the descriptive mineralogy lecture series here. I will send you the notes. Do you have? I think you should have. Do you have the access to the LMS? Because we get frequently alerts saying that no one has accessed it. LMS sends us alerts saying that this particular group of students have not accessed LMS so far. I think some of you have never logged into the system. Is it? So you need to log into the system. You need to log into the LMS and see what is posted there. Okay. Has anyone having difficulty in logging to the LMS? Is there anyone who did not? I mean, your username and password did not match, or some other error message came up while trying to log into the LMS. Have you tried to log into the system? I think many of you may not have logged into the system LMS. So you must log into the system LMS, right? And see what is posted there time to time, right? So I will post some information there, right? Some notes and some lecture notes that we have uh, already discussed so far, so that you will have to you will have to log into the LMS and then see on download or whatever. Okay. So if you find some difficulties in uh, accessing the LMS, please email to Miss Satya, right? I think you know already. So I'll put probably you know her contact details, right? So I'm just putting you the email of her. Right, so I just put her email there and ask for the help, right? If you find any difficulty related with LMS. Okay, right. So now we are going to stop the lectures, and with this, I conclude the descriptive mineralogy lectures, and Dr. Dharmapriya will continue with optical mineralogy part if he has to cover more sections, right? Okay, so if for any questions, do you have any questions related? Again, I'm asking because we are going to conclude. Before that, you can ask any questions if you have any related with this descriptive mineralogy part. Okay, if you have any questions, so you please email me even later. No problem. You can email me, and you can ask whatever you have the questions. Okay. So now I'm going to conclude the session. So on Friday, I think Dr. Dharma Priya will be continuing from 8.